Welcome everyone. So welcome to this new EURASIP webinar. We are very pleased to welcome today Nicolas Gillis. So Nicolas Gillis is a professor at Université de Mons and in Belgium. He is very well recognized for all his research about non-negative matrix factorization, for which he received several grants from FNRS in Belgium and also probably the most prestigious one, the ERC. So two ERC, one as a starting grant and the second one as a consolidator grant. So on this subject about non-negative matrix factorization, and he also wrote a book on this subject. So we are very pleased to welcome him today and to listen this nice webinar. So just to recall you, the webinar is going to be registered, and after that we will have a time for the Q&A session, but this Q&A session won't be recorded, so please ask any question you want. So thank you again, Nicolas, and the floor is yours.
Thank you very much, Nelly. Thank you for the invitation. It's an honor to be here today to talk about one of my favorite topic, which is the identifiability of a non-negative matrix factorization. So I worked on this topic since my master thesis, so a long time. And so this talk is trying to do, let's say, a short and personal historical tour on this question. So as you will see, it's obviously biased toward my own results and interests, but I'll be glad to get more results if you know some I'm not aware of. And please interrupt me during the talk if you have questions or if something is not clear. So yeah, first, so all this, many of these results I will present are joint work with many of my collaborators that I've had the chance to work with over the years. So I will mention them later in the talk, but yet it's important to mention this. So let's start with the beginning. So what is non-negative matrix factorization? So you are given a non-negative data matrix. So it has m rows and columns, and it's non-negative, meaning that every entry is non-negative. So it's a component-wise non-negative matrix. And you're also given a factorization rank R, which is typically much smaller than the dimensions of the matrix. And you're also given a error measure. So how you will measure the error between the matrix X and its low rank approximation, which I express as the product of two matrices, W and H, and W as R columns, H as sorry, it should have been R by N, R as R rows. So you want the product of WH. So this is a low rank matrix. This is a rank R matrix. And so what makes this problem very different from standard low rank matrix approximation problems is that you impose these two factors to be non-negative. So why is this useful? Why is this important? Because it gives you a linear dimensional reduction designed for non-negative data. So the way NMF is typically interpreted is in the following way. So each column of the data matrix corresponds to a data point. For example, it can be a spectra, it can be a vector of word counts in the document data set. It can be an image, it can be an audio signal, a spectrogram, the spectrogram of a time point in a audio recorded. And so NMF gives you a basis given by the columns of W in which you can reconstruct every data point approximately using a non-negative linear combination. So the fact that the basis vectors are non-negative allow you to interpret them in the same way you interpret the data. And the fact that the weights are non-negative only allows an additive combination. So you don't have cancellations. So here's an illustration. Also, of course, it gives you compression like all dimensional reduction technique. And so geometrically, so here's a very simple example where you have three-dimensional data points and you use a rank 2 factorization. So here you have two basis vectors, W1 and W2. And the fact that W is non-negative, it means that the data points, they should be approximated by the cone that is generated by these two vectors. I will come back to this later because the geometry of this problem is really crucial when you study the identifiability, as we will see. So why NMF? So why do we care about this non-negativity? So as I said, the main reason is interpretability. And as you may know as well, NMF was popularized by Li and Seung by a paper they wrote in Nature in 1999, which was mostly focusing on unsupervised data analysis. But actually, the NMF model came much earlier in quite applied fields. In particular, it arose very early in analytical chemistry. In that application, each column of the matrix X is the spectra of a chemical reaction going on at a time point. So you every, let's say, second, you measure the spectra of the reaction and you look what happens over time. So this is a spectra by time matrix. And so the W matrix will collect the pure spectra of the molecules that are present in the reaction. And the rows of H will give you the evolution of the concentration of each component over time. So in this application, W and H, they have a physical interpretability. W gives the spectra of the pure molecules, and H gives you their concentration over time. And similarly, in remote sensing, it also appeared very early. And in that application, each column is also a spectra, but the second dimension is a spatial dimension. So you take typically a picture, we show an example after, from a drone or from an airplane of an area. And so for each pixel, you have a spectra, which is a column of W of X. And then in the column of W, you will recover what are called N members, which are pure spectra of materials. And in H, you will get the abundance of each material in each pixel in the image. And so NMF allows to do unmixing. So in these two applications, NMF has a physical interpretation. So this is really why NMF became popular, because it really has a physical meaning. But it was also used in many other fields, in particular in probability and Markov chain, because in that case, the entries correspond to probability. So it makes sense they are non-negative, obviously. And also there are less known results, let's say, from our community, which is in combinatorial optimization. But I will not go into this today. And more recently, actually, NMF also been used to explain, to provide explanation for large vision models. So this is work by Thomas Fell. Actually, he won the French thesis prize from the French signal processing community last year. So if you're interested in these more recent applications of NMF, you can look up at his works. And so here are four famous applications of NMF. I will not spend too much time on the application side. I will focus more on the identifiability, as the titles indicated. So the first application, I mentioned it already. So here you have a hyperspectral image. So for each pixel, you have the spectral measurements, so typically between 100 and 200 measurements. And what you want to do is to unmix this image by identifying the pure materials. So here for this simple image are roughly six main materials, so road, grass, dirt, rooftops, and so on. And the rows of H will give you the so-called abundance maps. Each row corresponds to one material. So here is the road surfaces, the grass, the rooftops here, for example, and so on. Second application that is, of course, at the heart of signal processing is source separation. So here you have a simple example of a piano note with 3 notes. And you can represent it with its spectrogram, amplitude spectrogram. So for each time steps, you will have the spectral content at that time, at that moment. And if you perform NMF, in the factor W, which is shown here, you will get the spectral content of the nodes. And in the matrix H, you will get the activation over time, because the matrix is a frequency by time matrix. So the W matrix will be a frequency by node matrix, and the H matrix will be a node by time matrix. And so you decompose like this the signal automatically. Of course, in practice, you need to add constraint, regularization to get good results. But this has been used a lot, of course, since neural networks have appeared. They've also become very popular for this task. But NMF is still used, and it has the advantage to be very easily interpretable. And the two applications that were present in the Li and Seung paper, the first one probably is the most famous one, is about extracting facial features from facial images. So each column of the matrix X is a facial image, like here. here it's vectorized, but here I show it as an image. But so you vectorize it. So each column is one vectorized image. And when you do NMF, the columns of W will extract facial features which are non-negative, easily interpretable, and H will tell you which facial feature is active in each face. So, for example, for this face with a mustache, you can see here high value. So here you have the mustache is made of these two facial features. And the last application, which is also quite famous, regarding NMF, is a topic modeling, extraction of topics automatically. So here, each column of the matrix X is a document that is represented by a vector of word count. So each row corresponds to a word, each column to a document, and each entry is a number of times, for example, that the word appears in the document. And because the topics, the bases are non-negative, you can interpret them as topics. So these are a set of words that appear simultaneously in many documents. And the rows of H will tell you the matrix H will tell you which topics are discussed by which documents. So this is you can see this as a kind of a relaxation of k-means clustering. So here you have a soft clustering because a document can discuss several topics. So this is my favorite problem, the negative matrix factorization. So given a matrix X, you want to compute WH, which are component-wise non-negative. So as I briefly mentioned, there are many applications for this model in signal processing, also in machine learning, and as I mentioned, in combinatorial optimization as well. And there are many research questions. So as I said, I'm working on this for a long time now. So of course, there's a question, can we solve this problem? So without the non-negativity constraint, it is just an unconstrained logarithmic matrix approximation problem, which you can solve via the singular value decomposition. Unfortunately, with the non-negativity constraint, the problems become NP-hard. This was shown by Steve Avazis a long time ago in 2010. But as we will see, there are some venues to go around this. Then there are a lot of people who have designed, including myself, algorithms to solve this problem, either approximately or sometimes you can provide guarantees. But today, I will not talk about that. I'll talk about identifiability, which is a question of when are the factors W and H unique. So for example, for the small example I show here on the slide, the solution of NMF for this matrix is not unique. The rank 2 NMF of this matrix is not unique. I show you two different solutions. And I will define very briefly, very soon, exactly what I mean by unique. Because of course, as in all matrix factorization problem, you always have a permutation ambiguity. You can always permute two columns of W and two rows of H and get the same solution. And there's also a scaling ambiguity. I can divide this column by 2 and multiply this row by 2 and I get the same solution. But beyond these two unimportant ambiguities, I want a unique solution. So here it's not unique because you see here, there is these two columns. They are not permutation and scaling of these two columns. So these two factorization would be interpreted in a different way. So yeah, this is the definition. So an NMF is identifiable, essentially is unique, or some people say essentially unique because there is this scaling and permutation degree of freedom. If and only if any other exact NMF of the same size with the same number of factors can be obtained by permutation and scaling. So another equivalent way to write this. So any other factorization, WH of this W star H star factorization, you can always recover it as a permutation and scaling. So this is very standard. So please don't hesitate to interrupt me if something is not clear. And so this is very important in some applications. It's not crucial in all applications, let's say, but it's really crucial in some applications, in particular in analytical chemistry, because we really want to recover the true chemical compounds interaction as well as their evolution over time. In audio source separation, same thing. We want to recover the true sources, the true, for example, notes in the piano sheet. We don't want to recover an equivalent factorization that does not correspond to a the physical sound. And same for hyperspectral and mixing, where we want to recover the true materials and their abundances. And so it's very important to know whether the decomposition we compute is unique, because if it's not unique, then we don't know what we get essentially. So this is the goal of this talk. Try to introduce you to this topic, or if you know it already, to give you, hopefully you will learn a few new things. You let me know later. And this is the plan. So I will start with the geometric interpretation. I will first discuss full identifiability without any further constraints. Unfortunately, most matrices do not have a unique NMF. And so what we need to do in practice is to add either constraint or regularization, which I will discuss after that. And then I will finish with a so-called partial identifiability result. Even if the NMF is not unique, we may have some partial identifiability results that are possible to derive. All right, so let's go a bit more into a bit more technical details. So here I will focus mostly in this talk, although later I will talk about approximations, but I will first focus on exact decompositions because it's already hard enough to discuss identifiability of this factorization. It's even harder if you have approximation results. So, so here I assume an exact decomposition. So under this exact decomposition, you can always renormalize the data. So essentially, you will divide each column of X by its L1 norm, and same for the columns of W. And by this you can do by the scaling degree of freedom. So I divide each column of W by its L1 norm. So in this case, it's because they're non-negative, it's just the sum of the entries. And I scale H accordingly. Same for X. I can multiply on the right-hand side X by the 1 divided by the L1 norm of its columns to get an equivalent factorization. So I can assume without a lot of generality that X and W are column stochastic, meaning the entries are non-negative and sum to 1, which I write like this. So E is the vector of all ones. I know it's not always a standard notation in linear processing, but this is used a lot in numerical linear algebra. So E is the vector of all ones. So X is column stochastic, so mean E transpose X is E transpose, and same for W. And so now if I write my NMF and I put E transpose in front, you can see directly that E transpose H also has to sum to 1. It's quite logical. The columns of X, they're on the unit simplex. The columns of W are also on the unit simplex. And because the columns of X are conic, meaning non-negative combination of the columns of W, this conic combination also have to sum to 1 to remain on the simplex. And so this is a nice geometric interpretation. Each column of X is a convex combination, meaning a linear combination with non-negative weights that sum to 1 of the columns of W. So it means that the convex hull of the columns of X is contained in the convex hull of the columns of W, and the convex hull of the columns of W itself is contained in the unit simplex because W is non-negative. I mean, the columns of W are stochastic. So this is quite interesting. So NMF, you are given this polytope. It's just the data points here that you have normalized. On the right, you have the unit simplex, and you have to find a polytope that is nested in between these two given polytopes. And so the NMF problem is equivalent to this geometric problem of finding a nested polytope. The convex hull of the columns of W is nested between two polytopes. One is the data points, the convex hull of the data points, and the other is the unit simplex in dimension M. So you have to be careful here, and this has led to confusion in the literature sometimes, because the dimension of the inner polytope, so the convex hull of the columns of X, is the rank of the matrix -1, but the dimension of the simplex is M -1. And so these two polytopes might not have the same dimension. So in this illustration, they have the same dimension. It's just a very simple case where M equals 3. It's a trivial case. It's not very interesting, but just to show you visually what it gives. So the blue are the data points. The red is in between is the convex hull of the columns of W, and the gray one is the unit simplex. And so this geometric interpretation was discovered very early. I put some references that they may have. There may be earlier references. For example, in also hyperspectral and mixing literature. But this connection was made quite early. I mean, it's relatively simple to derive from the non-negativity constraints. So let me go on to full identifiability on full identifiability now. So I will present necessary and sufficient condition, and then I will look into more details the small rank cases, rank 1, 2, and 3. Another assumption I will make, so I told you right now I'm looking at exact decomposition. Another assumption I will make that is very, very typical in signal processing is to assume that the basis has the same rank as the data points, and that is the non-negative rank, the size of the non-negative factorization I'm looking at. So I'm assuming the basis, the columns of W, they have the same rank as the data points. But this is not, this is a restriction. So it's not always true that this will hold. So this is a quite famous example in linear algebra literature. So you have this 6x6 matrix. It's a linear Euclidean matrix. So each entry is I minus j squared. And this matrix, you can write it using a rank 5 non-negative matrix factorization. And so we say that the non-negative rank, so this notation means the non-negative rank is the smallest number of factors that you need in NMF to reconstruct the matrix. It has a negative rank 5, so here's the proof. You have the decomposition. It could be rank 4, but at least it's not more than rank 5. But the rank of X here is equal to 3, but the rank of W is 4. And it turns out that if you impose that the rank of W can only be 3, meaning that it shares its column space with X, you cannot have an NMF of size 5. So it is really a restriction. So this is really a restriction. There are matrices for which you need the rank of W to be larger. And the reason is that you will need a higher dimensional polytope to contain this lower dimensional polytope. This is intuitively, it's not so obvious, and that's why there's been some confusion in literature. And here's the geometric interpretation. So the blue thing is the convection of the data points. So because the rank of X is 3, it's 2-dimensional. Then in pink, you have the convection of the columns of W, which is dimension 3, because the rank of W is 4. And in black, you have the convection of the unit simplex intersected with the column space of W. Otherwise, we could not see it. It would be 5-dimensional, which we cannot represent. But only that subspace is interesting because outside the column space of W, we don't care what happens because we cannot represent it anyway. And so you see, if you stay in the same subspace as the columns of X, you will need, it's not easy to see it, but you will need to have six polygon with 6 vertices to go around it, let's say. But with one more dimension, you can go around it with one less vertex. Okay, but from now on, I will assume that the rank of W is equal to the rank of X, which means that, and also I will assume that I'm looking for non-negative factorization of the same of size, which is equal to the rank of X. And so another way to write a uniqueness is like this. So an NMF WH is unique if and only if the only invertible matrix is Q such that you generate another NMF essentially. So WQ is still non-negative and Q minus 1H is non-negative. So the product W times H is unchanged and they remain non-negative. The only possibilities are permutation of diagonal matrices. So permutation and scaling again. And as I just mentioned, is equivalent to having the convection of X of W contained in between these two polytopes, so the convection of the data points and the unit simplex. Okay, first, let's start with a necessary condition, a relatively simple one. Actually, also this condition probably dates back from a long time, let's say, but at least an early reference is by Moussaoui, Brie, and Idier. A necessary condition to have a unique NMF is that the support, so no columns of W, the support of no column of W is contained the support of another column. So let me show this on an example. So here is an NMF. Is it unique? I ask you. And here we can say directly it's not unique because, for example, the first column, its support, which is the first 3 entries. So the support is the set of indices with corresponding to non-zero entries, is contained in the support of the second column. So you can remove from the second column a little bit of the first column and it will remain non-negative. Essentially, that's quite easy to realize. And so here, if you do it, for example, if I remove from the second column the first column, I get a new column here. And I can adapt the weights but in that case, it will be addition, so it will remain a negative as well, to get an equivalent, an equivalent factorization, but which is not unique because you have changed the pattern, so it's not a permutation and scaling of the original matrix. So this is a very easy condition to check. You compute an NMF if some supports contain other supports in the columns of W or the rows of H, you don't have unicity. One of the first papers that studied uniqueness of NMF was by Donoho and Stodden in NIPS in 2003, so a long time ago already. And they came up with a simple condition to have uniqueness. It's quite strong, as you will see. It requires that the matrices W and H contain a diagonal matrix as a submatrix. So, and the proof is quite, again, not too difficult. So these are kind of early results. The reason is that essentially the identity matrix has a unique NMF. Because the identity matrix, the columns of the identity matrix are the unit vectors of the non-negative hortant, which are extreme rays of the non-negative hortant. So you cannot express an extreme ray in the non-negative hortant other than with itself, by definition. And so you cannot express the identity matrix in an NMF in another way than this, plus, of course, permutation and scaling. So the identity times identity is a unique NMF for the identity. It's not easy to prove this, not difficult to prove this. And so, for example, if I show you this NMF, is it unique? The first thing you can do is to check whether in W and H you find a diagonal submatrix. In this case, of course, because it's an example, it happens. So in W, you have the first row correspond to the third unit vector, this row to the second one, and here to the first one. And same for H, you have these unit vectors appearing. And so this NMF is unique. And note that this implies that in X, you also have the identity matrix up to the permutation and scaling that appears, because here you will have in the matrix X a submatrix that is essentially a diagonal matrix. So from these two results, we can already say quite a bit. For rank 1 NMF, it's very easy. It's always unique. Every column is a multiple of each other. So there is only one way to select a basis. You have to take a column of W that is a multiple of the columns of X. You don't have a choice. So for rank 1, NMF is always unique. And for rank 2, actually, the two conditions I just described, so the sufficient and necessary condition, for the rank 2, they coincide. Because if the columns of W, they have different sparsity patterns not contain, support not contained in one another, and there are only two supports, then they must have somewhere a zero with a positive and vice versa. And so it means that W will contain the identity, the diagonal matrix as a matrix, and same for H. So for rank 2, it's very easy to check if the NMF is unique. You just have to check whether the matrix X contains a 2x2 diagonal submatrix. So this is an easy case, let's say. And geometrically, it's not too difficult to convince yourself because you have a cone that is two-dimensional, meaning that if you normalize the data point, like I mentioned before, it becomes a one-dimensional polytope, which is a segment. And so this will have a unique NMF if and only if essentially the extreme point of your segment are on the faces of the non-negative hortant. Because here, for example, it's not unique because you can, for one column of W, you can take any points on this part, and for the other one, any point here, so it will not be unique. That's why we need this diagonal submatrices in W and H to have uniqueness in the rank 2 case. And this is an if and only if, so it's a complete result. So the rank 2 case is resolved, let's say. And this was observed very early also in the community. So rank 3, this becomes more exciting, let's say, more interesting. So if you come back to my definition of uniqueness, the two definitions I gave here. So it's unique if there is no matrix Q such that WQ is non-negative and Q inverse H is non-negative, but it's not so easy to check. At least visually, it's hard to check. These are algebraic equations, not so simple. But the geometry is quite simple because here the rank of X is 3, so it means that its convex hull has dimension 2. And because we assume that the factorization has the rank of the matrix, we can restrict the column space of W to be equal to the column space of X, because X equals WH, and X has rank R. So you don't have a choice. The column space of W has to coincide with the column space of X, meaning that you can actually simplify the outer polytope in your problem. You can intersect it with the column space of X, so that this one will have also only dimension 2. So you have 2 polygons nested between one another, and you need to find if there is a unique triangle between the 2. If there is a unique triangle, the NMF is unique. If there is no unique triangle, NMF is not unique. For example, I give you this factorization. Is it unique? So you can check that at least the necessary condition is satisfied, because there is a 0 here and 2 positive there, a 0 here, 2 positive there, and so on. So it satisfies the necessary condition. It does not satisfy the sufficient condition to have the identity as a submatrix. In fact, X is positive, so it doesn't work. But we can geometrically actually construct these polytopes, these polygons in this case, because they are 2-dimensional polytopes, so they are polygons, and look if there is one triangle. Let's see. This is the example. So we have X, which is W times H, and now I have a simple function. This is provided with the code of my book if you want to play with it later on. And so the code will give you the 2-dimensional representation. If I can make it down in the yeah. Yes, I got it. So this geometric figure is equivalent to this NMF. So what do we observe? So the data points, they are the blue dots. There are 4 columns, so there are 4 points. The red thing is the unit simplex intersected with the column space of X, which has dimension 2. And the black squares are the columns of W. There are 3 of them. This triangle is in fact between the blue and the red squares. And the question is it unique? Is there another triangle? It's not too difficult to convince you there is no other triangle. You can try other construction. If I start from here, for example, it will not work. And so in this case, we can prove it's unique. In fact, there is a way to compute all solutions to check this. So let me explain how this can be done. So this problem is called the 2-dimensional nested polytope problem. And for this problem, there is a polynomial time algorithm. It was first derived by Cilio a long time ago, but not in the context of NMF, but in the context of computational geometry. Then later, an approved algorithm was developed by Agarwal and co-authors. And more recently, Kubias, Robeva, and Stonfeld, they got a simplified version, which says the following. So if there is solution, let's say the best solutions, so if there is a solution, so a triangle or a polygon between the 2 given polygons, there is at least one solution that contains either a vertex of the outer polygon or a segment of the inner polygon. So if I look back at my figure, so in this case, the solution contains this segment of the inner polygon. So now what can I do? I can take a red, I didn't do a movie, but if I move the square here above, for example, let's try to do it. So if I start from here, my triangle, I go here. Then I go here. Then I go here. You see, I cannot come back. So it means that if I start a triangle from here, it doesn't work. So I cannot make an NMF from this point. In fact, you can prove that once you choose a point, it's always best to choose a starting point on the boundary, and then to go, of course, tangent to the inner polygon. And what you can also show is that the function that maps you from here to here is actually piecewise concave, and then it means that the best points, or the one that will go further, are where the breakpoints arise. And the breakpoint, they in fact arise either when you take points that correspond to, if you take a segment of the inner polygon and you, like you do it here, you trace it like this. So these 2 points will be, if you want local solution, so from this point, I can go the furthest away by going around this inner square, inner quadrilateral. And so you can check in this case. So because this one comes back exactly here, any solution next to it will go not as far, and so you cannot make a triangle around it. And the other possible solution would be starting from either other points which are intersection here. So in this case, we would need to try this point here, like this, but clearly because there is less space here, you will not be able to come back as a triangle. And then you can try also the points here that intersect this segment with this. So start from here. So will it work? So it doesn't work. As I told you, it's unique, so you cannot come back. It's easy to see, you cannot come back. And then the other points you have to try is also the vertices of the outer polygon. And so if you start from here, can I do it? And again, you cannot come back. So that's why this one is unique. Okay, I hope it was more or less clear. And I have another example just to show it. It's from the paper of, I forgot actually from what paper. I have to find this information back. So this is another NMF. So it's interesting because here it's even a symmetric NMF. I will not talk about symmetric NMF, but it's also an interesting topic. So the question is this one unique? So again, it satisfies the necessary condition, but not the sufficient one. But geometrically, if you map this as a two-dimensional nested polygon problem, and you get this problem. So in this case, there are 6 columns in X, so you have 6 data points here. And it's not easy to see visually, but the intersection of the column space of X with the unit simplex also gives you 6 vertices. And in this case, it's not hard to see again that the only triangle that can fit in between is this one, and it corresponds to this NMF. All right. So for the rank 3 case, let's say the problem is more or less settled, although it's a bit more complicated than the rank 2 case, obviously. And so the question is, can we go further? Can we go to rank 4, 5, or 6? And unfortunately, the answer is no, because the 3-dimensional nested polytope problem, it's NP hard in general. So yeah, this is not possible. What is quite interesting is in analytical chemistry, they worked a lot on this problem of drawing all possible solutions. And for rank 3, you can do this by using the geometric insight I mentioned you. And they call this the Borgen plots because it's Borgen and Kowalski who introduced this. So you can actually compute all solutions by using this geometric insight on the nested polygon problem. If you go to higher dimension, you can just use a sampling technique. It becomes already, even for rank 4, it becomes already very complicated. So I see I'm going not as fast as I expected, but that's okay. I will probably not go over all the slides, but I'll share them with you if you're interested. So for me, I mean, well, this is very subjective. One of the nicest results, probably for me, the nicest result from my opinion, but this is debatable, is this result by Kejun Wang, Sidiropoulos, and Swami. That relax the separability condition from Donoho and Student to get unique NMF. So what is this condition? They call this the sufficiently scattered condition. And it requires, so the matrix H satisfies the sufficiently scattered condition if the cone generated by the rows or the columns of H, contains this sphere. Maybe it's easier with my second drawing. So here's a representation for R equals 3, so rank 3. So separability, if you remember separability, it means that the columns of H contains the unit vectors. And so the cone generated by the columns of H is the full non-negative orthan because it contains a diagonal submatrix. This is quite a strong assumption. So in the data analysis applications I mentioned, like in hyperspectral and mixing, it would mean that you need a pixel that contains only a single material. For each material, you will need that. But the sufficiently scattered condition is much weaker. You don't need to observe pure pixels or pure basis elements. You only need to contain this sphere tangent to the unit simplex. So this is the representation for R equals 3. So the columns of H, they are cones. So here I represent it as a convex hull by normalizing the columns of H, but it's equivalent. You need to contain this sphere. And they prove that if W and H satisfy this condition, then the NMF is unique. Note that this condition implies some sparsity because to contain the sphere, you need to contain the tangent points, and to contain the tangent points, you need to contain some points on the facet. So you need some sparsity. We know this is a necessary condition, so it's not surprising, but it's just to show you that it is consistent. So unfortunately, this condition is NP-hard to check. So all the conditions I mentioned before, they can be checked in polynomial time. It's not the case of the sufficiently scattered condition, but there are some ways to compute it efficiently because it's not polynomial, but it's only exponential in R. And R is quite small typically in practice. So even for large data sets, if R is small, you can still check if that condition is satisfied, but I will skip this. So, okay, so we are done with the first part. And so, as you may have guessed, I mean, these conditions are quite strong. That sufficiently scattered condition requires W and H to be sparse, which is not always true. Sometimes only one of the two is sparse. And so if you want to get identifiable NMF, you need to add regularization or constraint on the factors. So the first one that appeared in the literature is separability. So you will look for an NMF where the matrix H is separable. So this implies that in the data matrix X, you observe the basis vectors. So it's quite a strong assumption, but it gives you a lot. It gives you unicity, of course, if the assumption makes sense, and also it gives you a way to compute the NMF efficiently. So it's a strong condition, but it gives you, let's say, two nice things: identifiability and polynomial time complexity for NMF. And so this assumption makes sense in some application. I will go quick about this. So this is a way to compute the solution. So essentially, geometrically, what happens is that the data points, because of separability, they are in the convex hull of the columns of W, because H contains the identity as a submatrix up to scaling and permutation. And so what you need to do essentially from a geometric point of view is just to extract the vertices of the convex hull of X, which is not a difficult geometric problem. And so one way to do this is to use this successive projection algorithm. You extract the column with the largest L2 norm after normalization of the data points, which is always a vertex, because it's essentially it's a strongly convex function. It's always maximized at a vertex of a polytope. And then you project to the orthogonal complement, and you do this sequentially. So it's like a QR with column pivoting. And this algorithm is very simple, but it's quite effective, and it's robust to noise. You can have bounds on the noise. And if you want to know more about this, I have a recent paper that discusses the robustness of this algorithm. And so as I mentioned, the application of separable NMF are, for example, hyperspectral mixing, where you have pure pixels, so meaning for each material, you have at least one pixel containing only that material. In topic modeling, you need pure words, meaning words that are associated with a single topic. For example, if you see a zip code in a document, you are sure that it discusses signal processing. It's not likely it's used in other contexts. This I will skip. So as I said, separability is quite strong. And so again, SSC can help. We can relax separability to SSC. So the question is, given the blue points, the data points, can I recover the red crosses? So for separability, it's easy. You just find the blue points that are the most extreme, let's say. But for this one, it's not as clear how can you do this. And in fact, you can do it. And this is probably the second best result in my top results on identifiability of NMF, is that if you minimize the volume of a matrix that contains the blue points, you will get the red points, if the matrix A satisfies this SSC condition. So essentially, if the blue points are sufficiently well spread within the convection of the red points, minimizing the volume gives you the results, gives you a unique solution. So this was a result proved by 2 papers simultaneously, one with Xiaofu and co-authors, and another one with Lin and co-authors, and Kenma also was present. So he's one of the driving force of these results. And so what you will do, you will look for an NMF. So here on the right, you have the NMF with the minimum volume. So this is a measure of the volume of the columns of W. And if A satisfies the SSE, so if the data points are sufficiently well spread in the convection of the columns of W, then you can recover W using this. So there's been many use of this. In practice, of course, you have noise, so you use it as a regularizer. So there are 2 problems here. The first one is that it's NP hard in general. So this problem, as opposed to separable NMF, here it's hard to solve. And also, there was no robustness results. Actually, this is a French robustness, so it should have been robustness anyway. Close enough, we say. And so this, in fact, this question was asked in these 2 papers, and luckily with some 2 of my postdoc, Subayan Sa and Giovanni Barbarino, we were able to prove end of last year that in fact you can have robustness for minimum volume NMF. But for that, you need to strengthen a bit the SSC condition. So we introduce a P-SSC condition. So this P is a parameter. So if P is equal to square root of R minus 1, we get the SSC. If P is equal to 1, it's separability. And in between, it requires that the convection of the columns of H contain a sphere that is essentially bigger than this one. And the P will go from the tangent sphere to the sphere that contains the full thing. And under this stronger condition on H, we can get robustness. So for the sake of time, I will skip it. But so if the data points are sufficiently spread, so more spread than in the noiseless case, but not separable, so there is something in between that gives you robustness for the decomposition. But it's also interesting that you can also look at a dual approach and maximize the volume of H. And so you get also similar results. You get also identifiability. So this was a very nice paper by Tatley and Erdogan, because actually they generalize these results to any what they call polytopic matrix factorization. So the columns of H do not need to belong only to the unit simplex, but they can belong to other types of polytopes. So this is a very nice paper if you are interested in this topic. And this, in practice, we observed recently that it works better than the min-vol, because min-vol in practice is not so easy to tune because it tends to make W rank deficient. While maximizing this will not make H rank deficient. It will try to make it the rows orthogonal, so make W sparser and sparser, but not rank deficient. So you will never generate rank deficient solution with maximum volume NMF. An open question for you: is it robust? Is it do you have robustness results for this? We don't know. So this would be an interesting topic for research. So this I will skip. You can also get identifiability via sparsity. Essentially, you identify the facets sequentially by solving mixed integer programs. Again, you have a subprogram that is hard to solve, but you have identifiability at the end of the day. So essentially, the condition is that you need sufficiently many points on each facet, but you don't need to contain the sphere. So it's kind of a different condition. So the one does not imply the other. Okay. And the last thing I wanted to talk about, I have maybe 1 minute left, is partial identifiability. So sometimes the NMF is not unique, and in practice, I mean, it's okay. I mean, it's not unique. What can you do? You can still get some partial identifiability results. So I give you this NMF. So here's W and here is H. So each curve here is a column of W, and here each curve is a row of H. Okay, this is not unique. For example, you can see easily it's not unique because, for example, the support, what is it? Yeah, the support of the blue one contains the support of the orange one, for example. So it's not unique. It does not satisfy the necessary conditions of sparsity I mentioned. But can we say something about partial identifiability, which I define as, so a column of W is partially identifiable, is identifiable if in any NMF you have to recover that column up to scaling. And there is a very simple way to check this. Actually, I realized later, after this paper, I realized that the result was actually hidden in that paper. But luckily, we had other results in that second paper. So what is the condition? Let me show you an example. So a column of X of W is unique, meaning it has to be recovered by any NMF. If you look at the zeros of the columns, then you look at the remaining matrix here. So this submatrix. So this submatrix must have rank R minus 1. So in this case, rank 2 is the case. And it has to have a separable, it has to be separable in H. So it means this column has to appear in X. And in that case, you can prove that this column is unique. It has to appear in any NMF. It's not very hard to prove actually, because geometrically it means that essentially W, that column of W is a vertex of the inner polygon that touches a vertex of the outer polygon. So to have a polygon in between, you need to touch that vertex. So you don't have a choice, you have to pick that vertex. That's the idea geometrically. So if I come back to this example, can I identify unique one of the shapes that are unique? So you have to have so for example, if you look at the blue here, it's positive while all the others are zero. So the blue curve, it appears alone, let's say, in this part. So this is the selective window assumption. And then when the blue is zero, the other ones are positive, and you can check its full rank. So this means that the blue one is unique. So this blue one has to be recovered by any NMF. And you can do the same for the red, the yellow here. The yellow here it's positive, and the others are zero. And when yellow is zero, the other ones are positive, and they are full rank. And you can also do it the other way around for H. And so for any NMF, you will recover the blue and yellow columns of W and the green row, let's say, of H. And this I can show you quickly in a MATLAB demo. If you allow me, almost done. After that is the conclusion. So here I have this data set. I compute an exact factorization, and then I display it. As you can see, it's not unique. My solver found another solution, but you can see, maybe you cannot see, but two of the columns were recovered, like the blue one was recovered. So the dashed one are the new ones, like the one that I computed numerically, and the other ones are the initial ones. This one and this one, this one and this one, they've been recovered. The other ones, they are not unique, so they are not recovered. And same for H. As we have seen, this one was unique, and so it's recovered, but the other ones are not recovered. All right, let me conclude. So hopefully I convinced you NMF is a powerful data analysis technique. Uniqueness is important, key property in some applications. Unfortunately, it's not often unique. And so we may need to resort to constraint or regularize NMF models. I mentioned separability, minimum volume, sparsity, but there are other ways. Separability is nice because it's polynomial time, while the other approaches, minimum volume, sparsity, they lead to NP-hard problems. So there is still a bit of a practical issue, although in practice, the algorithms that we use, they work well. Partial identifiability, it's only been studied very recently, so there's not many results. So if you're interested, this could be a research direction. And also there are some extension to tensors. Of course, if you look at the CPD, it's already unique in the unconstrained case, so there is not much to say. But for non-negative Tucker decomposition, we have a recent paper discussing how non-negativity can make Tucker unique. And so if you want to know more about NMF, as Nelly said, I have a book on the topic that you can download for free on my webpage. And I thank you for your attention.
Thank you very much, Nicolas. So thanks for the talk. So now is going to be the time for Q&A questions. So I remember to all of you that this session of Q&A question and answer won't be registered. So feel free to ask any question.